Professor John Wetlaufer. Could you summarize what this year's Nobel Prize is about?
Yes. The overarching theme is what we could think about as an umbrella of complex physical systems. Of course, when we look out in nature, there are plenty of complex physical systems. But what emerged from the committee's work was the duality between the study of Earth's climate, which is complex on scales from millimeters to the size of the planet, and Giorgio Parisi's work, on the other hand, which actually does come back to climate, as he mentioned in the press conference, but he's building from the disorder and fluctuations of complex systems at their microscopic constituents and predicting the behavior, whereas the work of Shukuro Manabe is taking the components of individual processes and knitting them together to predict the behavior of a complex physical system. And Klaus Hasselmann sees both the value of the microscopic understanding and the implication of the macroscopic climate problem. And so I think that's a summary, even though we've divided the prize between the climate part and the disorder part, they really are linked.
Hello, everyone. Welcome to the Birla Industrial and Technological Museum's online lecture series celebrating the Science Nobels 2021. You've just heard Professor John Wetlaufer, member of the Nobel Committee for Physics, speak about this year's awarded discovery. Complex systems are characterized by randomness, disorder, and are difficult to understand. This year's Nobel Prize in Physics recognizes new methods for describing them and predicting their long-term behavior. Distilling complexity. Simply put, that is exactly what we intend to focus on today. We look forward to your reactions, and the YouTube chat box will be open to receive your questions. We'll try to take them up at the end of the session. Now, to discover how we see clear patterns emerge from noisy systems, we have with us a very special guest. I would request Director BITM, Mr. V.S. Ramachandran, to introduce us to him and initiate this discussion on coding the chaotic. Over to you, sir.
Thank you, Aditi. Good afternoon, and a warm welcome to BITM's online lecture series, the Science Nobels 2021. Highlighting the importance of this year's Nobel Prize winning work in physics, we are excited to have with us today Shri Pallab Roygupta, teacher of physics, Greenpoint Academy, and a freelance science writer. That too, he is even writing in Shaastra magazine, IIT Madras. Welcome you, sir, on behalf of BITM Kolkata. An independent thinker with a curious bent of mind, Shri Roygupta has been on the winning team in Science Communicators Hackathon at CERN 2020. Oh, great. His passion is amalgamate science with creativity leads him to outreach activities for LIGO, Indian Science Communication Team, and International Particle Physics Outreach Group. Shri Roygupta is a prolific writer with contributions to science magazines like Vigyan, Anveksha, Gyan O Vigyan, and LIGO, India Gravity Matters blog. He is also a regular speaker at All India Radio, Science Popularization Division, and has participated in numerous panel discussions at home and beyond. On behalf of BITM, we welcome you, dear Sri Roygupta, to deliver the talk Disorder, Spin Glass, and Chaotic Climate, Hidden Rules that Riles Complex Systems. A bit longer title. Fine. Welcome you. The floor is yours. Thank you.
Thank you, sir, for these kind words and beautiful introduction. This is my honor to present talk in front of August gathering of BITM. BITM given me this incredible opportunity to say something on the Nobel Prize of Physics for this year, the topic on which that is given. So let's start. Am I presenting?
Not yet. Yes, it's loading. Yes. Please continue.
Okay, thank you. The title of is Disorder, Spin Glass, and Chaotic Climate, Hidden Rules That Riles Complex Systems. Let's start with some famous pictures. I'm quite sure that many of you among the audience can immediately recognize this picture and also can recognize the movie from which it has been taken. And the movie is The Day After Tomorrow. That was released in 2004. It has been depicted in this picture that the entire planet experienced a new ice age, an ice storm, which is a consequence of drastic climate change. Though the climate scientists, they warned the policymakers, but nobody was ready to listen to them. Let's go to the another picture. And many of the youngsters can recognize her immediately. Yes, she is Greta Thunberg, an 18 years old Swedish environmental activist. When she was at 15, she held sign saying a school strike for climate to pressure the government to meet the carbon emission so that that it can reduce the carbon emission in the weather, which can protect our climate for future. She is an inspiration for thousands of young minds and young people across the globe. So from these two pictures, both of these pictures says about climate change, the threatening of climate change. But then also, many of us, many of around the globe don't believe in this theory. But this time, Nobel Prize Committee picked up this topic for the Nobel Prize of 2021, and they have chosen two climatologists, Klaus Hasselmann, Secura Manabe, and the another one is Giorgio Parisi, who is also connected to the work underlying, but is mainly from complex systems. This decision of Nobel Committee, I believe, that will change the direction of mind of the policymakers across the globe. The Nobel Prize, that is, the value of Nobel Prize is $1.1 million, that has been splitted among these three stars, like Giorgio Parisi got half of the prize, and Klaus Hasselmann and Secura Manabe got the second half. Let us start with the work of Secura Manabe and Klaus Hasselmann, and for their trailblazing work in meteorology. Let us start with some background story. Thors Hans Hasselmann, he's the chair of the Nobel Committee. He said that though the two prizes were separate, there was a common theme that has to do with disorder, that has to do with fluctuations, and how disorder and fluctuations together, if you understand it properly, can give rise to something we can understand. What is climate? Most of us, we know about the weather. We talked about rainfall, we talked about temperature. Now, a climate is average weather in a given area for a longer period of time, that we may know. Many of us know about this fact. What are the factors? There are many factors affecting the climate: ocean, atmosphere, space. And within this ocean, atmosphere, and space, many things are there: heat, radiation from the sun, snow and ice, rainfall, clouds, wind flow, ocean currents, and many more. And also human activities. Let us go back to the past and see how that climate research chronologically evolved. In 1896, Santa Arrhenius develops a climate model, and he describes that the carbon dioxide influenced the climate very much. He was the first person who recognized this fact. In 1961, Edward Lorenz connects chaos and weather after his weather simulations very widely from run to run. Now, in this point, we cannot understand. So before going into the detail of Ed Lorenz's work, let's talk about a little bit of history, background history of his work. During the 16th, 17th century, when Newton was the hero and Newton's laws of motion which can govern the laws of the universe, they believed, using Newton's laws of motion, that it can be determine the position of any object, and also can we understand the planetary motions. At that time, it was in the thought of everyone's mind that we can predict the future profoundly using Newton's laws. But that theory was overthrown by Henri Poincaré. Henri Poincaré pointed out a problem. That problem consists of three bodies instead of two bodies. When three objects swirling around each other, their motion is not very much simple. Even there is no such simple solution to this motion. And that was the first thing that Henri Poincaré determined, that was three-body problem. And that was the beginning of the disorderness or chaos. Now coming into the point of Ed Loren's work, chaos come into the focus in 1960 when meteorologist Ed Lorenz tried to make a computer simulation. He was working with a simple model of Earth's climate, and he found there are 12 parameters, so that he had 12 equations. And he put for simulation this 12 parameters, and for each parameter he's getting some series of numbers in 12 row. And he set for the simulation and take its printout. In the another run, he thought, okay, let it simplify the process. And what he done, that he start from the mid way of the printout and again starts simulate the data. And he went for a coffee. After coming back from a break, he found an enormous different thing. He found that for a small change, there was a huge difference in the later on data. Initially, he thought there must be a problem in the computer. But after observing it properly, he found no, there is no problem in the computer. Rather, the later on data is being changed drastically on changing the initial conditions slightly. Ed Lorenz simplified this 12 parameter into 3 equations and make an attractor just like a 3-body problem. And what he got this kind of structure after simulating this data, that he found that if we know the initial conditions, we can predict their motions, we can predict the future of their paths. And which we can see in the second picture as a log structure. You can see there is a spiral structure. But if we change initial conditions slightly, the motion of the it is much more famous name, and that is the butterfly. Because the spark simulation looks like the wings of the butterfly. The motion is, if you know the initial conditions, if you set the initial conditions, it actually predicts the future. But if you slightly change the initial conditions, that will change the future of the past drastically. And that notion was so attracting to the scientific community, even in the non-scientific community as well. If you search, then you will find that there are so many movies and documentaries on this particular effect, that is butterfly effect. In the name of this, you can see many movies and documentaries. Ed Lorenz started this idea of disorderness in climate, introduced chaos
I'm sorry, there might be a technical problem. We'll try to connect with the speaker in a little while.
But how?
Sir, we
Yes,
we got logged out. So can you please repeat the last session once more? The last part, I guess.
just a second.
Yes.
From this, hello, am I audible?
Yes, you're audible, but are you? Your presentation has not been shared. I think you need to
Well,
share it.
well, from which slide can you see?
We were at the chaos disorderness slide, three body problem.
Well, am I presenting?
Yes, you are. Uh, it's the entire screen, I think. Yes.
This one?
Next one. Yes. We have been through this. The latter part, I think, you need to repeat. The beginning
Have
part.
I said the Lorentz attractor? Well,
Yes. Yes.
okay. So sorry for the inconvenience. So that I was talking about the Ed Lorenz work. Ed Lorenz simplified this 12 parameter into 3 parameter, and he set it for it run for the simulation. And what he found a beautiful path structure. If we change the initial conditions, immediately the path structure changes. It will change the track, and which is completely a new track. But if we stick to the initial conditions, that initial conditions lead us to the deterministic future. That reminds us about the Laplace demon theory. Once Laplace was a mathematician who predicted. Uh, he thought of a very intelligent person that who can determine the future by using the present parameters. If somebody knows all the present conditions properly, he also can predict, he can determine the future of any event. And later on, this was famous as a Laplace demon. Anyways, that Lorentz attractor, at the same time it is deterministic, and at the same time it is chaotic. So let us move to this point that this particular path simulation, it's very much looks like the wings of the butterfly, and it is very much famous as the butterfly effect. It says that the minimum change in the initial conditions can create a huge distraction, huge drastic change in the later on data or in any event. And that attracts so many people around the world from scientific community and from the common people. And that is so famous that if you search, then you will find many movies in this name, in this concept, documentaries, been depicted in this concept. So the Ed Lorenz was the pioneer of introducing the idea of chaos in the climate system. Now let's start with the work of Sekuro Manabe. His work in 1967 was pioneering and trailblazing. For his work, he has chosen for the Nobel Prize this year. What was his work? What was his prediction? I just go with his own words that he was loved to watch the sky. He was born on 21st September 1931. He fell in love with sky, the movement of the clouds around the sky. And each and every day there are different clouds, different colors. And that insists him to took meteorology as a subject in his career. Sekuro Manabe passed out from Tokyo University, and he was working in Japan, but that time there was very less opportunities in Japan, and people was doing the calculations of weather forecasting and all these things with their hands, and predictions was so pathetic and funny that people don't believe in this weather persons. And if you remember, even if you remember your past also, even in 15-20 years ago, that I can remember one event that before puja there was heavy rain for 3-4 days, and the next day forecasting was it will continue to be rain for another 72 hours. And that very day we celebrated, because that we was quite sure about that the next day there will be no rain, and it was there was no rain in the next day. So that kind of weather forecasting was there even in 15-20 years ago also. Sekuro Manabe was literally frustrated from this kind of forecasting, and that time he took this opportunity and to go to the America, and he joined the team led by Joseph Smirnitsky in US. And that time there was a huge work was pioneering by John von Neumann, another famous mathematician and thinker. He used the computer and bring a lot of meteorologists to calculate the weather forecasting using the computer. Manabe took this opportunity. And his work, what he did, he was a very, and that kind of person, he was not satisfied with the simple weather forecasting. He was thinking for a global picture, that can we predict our future? And that idea led him to the idea of making one-dimensional climate model. He took some factors, the radiation, the atmosphere, the hydrosphere, the the waves, and the human activities. And he found a very interesting result. He found that mainly human activities and other things which are present in the nature, like the greenhouse gases like CO2, methane, carbon dioxide, methane, and water vapor, they create a layer within the atmosphere, and that lower layer of the atmosphere trapped the radiation. If there is no atmosphere, what will happen? The radiation comes from the sun, it will reflect to the space again. But due to the presence of this greenhouse gases around the earth, all this radiation is being trapped, not all, the amount of radiation is being trapped within this layer of these greenhouse gases and again reflect back to the earth. What is happening? You see that there is a trap of that the layer of carbon dioxide and methane and other uh, things present, that water vapors and all those, it trapping the radiation, and the upper layer which is cool, and the lower layer is completely warm. And the consequence is it's rising the temperature as human activities, that like that from the cars, from the uh, from various carbon emissions from various places, it's increasing the carbon dioxide. Even he predicted, if the carbon dioxide emission if get doubled, then the temperature will rise up to 2 degrees, and that was alarming for us. His idea leads us to this consequence, global warming. And this picture has been taken from one very famous movie, Kadbi Hawa. The drought and the heat death. After decades later, this person, this handsome guy, Klaus Hasselmann from Max Planck Institute of Meteorology, Germany, he took this idea far more ahead. Manabe also created the 3D model, and inspiring by that model and independent from his independent work, he also found that weather and climate, they are very much related to each other. He found a relation how weather is very much chaotic. There is no certainty in weather. Each and every day the weather can be changed. If even in many places, suppose here today where I am sitting, if it is cold, then in that 100 kilometers away, that's very hot. Or in some places it's raining, in some places it's drought. So weather is completely chaotic over the earth, around the globe. But then also this chaotic data, if we repeat for a longer time, we can create a model which can be deterministic. Again, the idea of Lorentz. At the same time, it is deterministic and chaotic. He found that using this chaotic data of weather, he produced a stochastic climate models in 1976. In some places, it's rapidly changing, and in some places, it's smooth. But over the years, we can have a prediction. And the prediction was that he found that yes, the earth is heating up. There is increasing in greenhouse gases. And yes, the most important factor in this process is human activity. Manabe and Klaus Hasselmann proved that the human activity, not the nature alone, the human activity is creating this this massacre, and we are creating our own death. We are writing our own death. After listening to the story of the Klaus Hasselmann work and Manabe, and also we started with the activists' work, the movie. What we can do we can delay our doomsday. If we think more about climate, we can delay our doomsday. That is the message, I think, from the Nobel Committee by giving this prize to these two fellows. The another part of the story lies in the complexity. Before that, Klaus Hasselmann's work, he connect his work with the climate weather, that it is depends on the sea waves, and if we can study the sea waves properly, that we can predict the climate in future properly. And on his work, on the basis of his work, by getting inspiration from his work, NASA sent his first CSAT mission, and also Europe sent his first Earth observation mission. So he's the father of Europe's first Earth observation mission in the another way. Let's go back to the second part of the story. Next level of complexity. Spin glass. If you are thinking that what is spin glass, and after thinking, if you think like this, no, I'm sorry, this is not the idea. Spin glass is neither spin nor a glass. Spin glass is actually a metal alloy where iron atoms, or you can use manganese atoms, are randomly mixed up with copper atoms. The term spin in quantum level, an atomic level, it's not like spinning of a ball. It's an orientation, or in physics word, it is a magnetic moment, a direction. If we create this kind of alloy, this metal alloy, where the orientation of this magnetic lines and this magnetic spin, they are randomly oriented. So for example, we can take an example of a 3D lattice. Suppose in the three corners of a 3D lattice, a triangular lattice, suppose this is spin up, then spin down. Spin up can interact with spin down, but what we can keep here? We cannot keep spin up, we cannot keep spin down, because they don't, the two of them, they don't like each other. So they will repel. So what will happen? So this condition is called magnetic frustration. And it has been found that though there is magnetic frustration, though there is randomly oriented magnetic spin, these structures are very, very much stable. And it was a fallacy to the whole scientific community. And here is the genius of Giorgio Parisi, who is the professor of Sapienza University, Rome. Let's start with some background story. In 1950, John Wen and others, they study the classical spin glasses and disordered magnetic states of matter. In 1973, two persons, David Serrington and Scott Kirkpatrick, introduced a model to describe the spin glasses, but they failed to solve it. They found, yes, there is a stability, though there is completely disorderness in magnetic spin, but this structures is very much stable. And they found that there could be an infinite possibilities, and they could not solve the whole problem. Now, as I said, spin glass, why it is said to be glass? Because glass is something, is an amorphous solid, where the orientation of the crystal structures are not very much oriented, they are disordered crystal structure. So here is the analogy from this disorderness in magnetic spin. That's why scientists use the term glass over here. Now you can see the crystals are very much oriented. All the atoms are oriented in a proper way. In glass, you can see that the orientation is not proper. In ferromagnet, all the magnetic moments, all the magnetic spin, they are oriented in the same direction. But look at the spin glass, all the magnetic spin, they oriented randomly. Physicists observed, you can see this GIF, that this structure, though there is completely randomness in magnetic spin, that this structure is completely stable and skipping its stability by changing its position randomly. Giorgio Parisi found a superb model. He introduced a beautiful idea. Instead of solving it or try to solve in a simple, by using a simple way, he made it more complicated. Why I'm saying this? Because he replicate all the possibilities of the spin orientation in groups and subgroups and infinite groups, and that his work is known as replica theory. That he replicate all the spin structures, and again he replicate into subgroups, and after replicating again and again various spin structure, various possible spin structure, and all the spin structures are stable, finally he found a underlying symmetry, underlying a pattern within this chaotic world. That was his genius. That is the beauty of his work. He didn't try a shortcut. He made it more complex and found a beautiful result, underlying result. He break it more and more. And what it tried, that it has been said that he said that you can simply simplify one of the most difficult steps by considering not a single configuration of spins, but a huge number of replicas of the system with the same disordered couplings, but potentially different individual spins. This might seem like it is making things much worse by adding still more complexity. He added, rather, it's still more that he added more complexities, and at same times happens in math. Writing equation in these terms lets you rearrange the resulting integrals in a way that makes them much easier to solve. If you look at the picture, and this is how he replicate all the stable spin structure, and he found an underlying pattern. His work opened up a new field which is known as the complex system. He is the pioneer of the complex system. His work is applied to many complex real-world systems in atomic structure, biology, mathematics, machine learning, brain network, even in climate. Also, even to understand the behavior of the flock of the birds. Using his ideas, if you see that the video that it's very much available in net, that this flock of the birds are very much random, their motion, but the work of Parisi allow us to predict the motion of this flock of the birds. Now here, now what he did, why his work is so beautiful, though it is really complex, really random, but then also you think the information, what we talk about, it is random. When we have more information, it is random. It cannot be oriented. And we require more information. Suppose you have a picture. If you pixelate it, each and every pixel carrying the information of the picture, and each and every pixel is important. Similarly, to understand the universe is not very much oriented. It's a oriented structure, but behind it there's a lot of complexities, lot of randomness. And because of its random, our motive is to find out the beauty from this randomness. That is how that chaos, the definition of chaos tells us. Chaos theory is an interdisciplinary theory of branch of mathematics focusing on the study of dynamical system whose apparently random states of disorder and irregularities are actually governed by underlying patterns and deterministic laws that are highly sensitive to initial conditions. Again, highly sensitive to the initial conditions. If you know the initial conditions, you can predict. But here is the fallacy. We don't know that initial conditions will be same or not. That's why we cannot predict so many things. We cannot predict. Just few days back, I was discussing this idea with one of my friend from literature background, and he pointed out with a beautiful idea with a poem. Actually, it's written by a very famous Bengali poet, Shakti Chattopadhyay. I cannot restrict myself to share this beautiful poem with you people. Just emphasize in the second stanza that where he has been emphasizing that if we know the rules of breaking, there is a science even in breaking also. Then also when you are breaking, you are going into more complex. But then also if you know the rules, then you will find so many beautiful things in it. And sometimes breaking is much more beautiful than the construction. I'd like to conclude my talk here. Thank you so much.
It is fantastic to see the work of climate scientists rewarded with this Nobel Prize in Physics this year. Manabe was reportedly actually gobsmacked when he had heard that he had won the Physics Nobel. He's reported to have been saying, but I'm just a climatologist. So climate is definitely changing, and so should we. So thank you, Mr. Roygupta, for sharing the secrets of this chaotic but wonderful world with us. Now, this award comes before a pivotal climate meeting, the 26th United Nations Climate Change Conference, due to take place in Glasgow in November. What message do you think this carries to the world leaders across the board, like a climatologist winning a physics Nobel? Is there some kind of a message that the Nobel Committee wants to convey?
I think I already mentioned this point that yes, I think Nobel Committee pointed out this idea to think that we should think that mainly the policymakers around the world, they should think about that how they can implement some rules to restrict many things and to protect our climate. And as I said, that we can only try to delay our doomsday. Doomsday is obvious, but we can only delay that.
Right. So the message is loud and clear then, that global warming is resting in solid science, and it's time to take action. It's high time actually we did something about it. So we come to the end of our session here. Thank you to the students, teachers, friends, and patrons of BITM who could make it live to this session. We covered this year's Medicine Nobel winning work in yesterday's session and are scheduled to discuss the implications of the latest chemistry Nobels tomorrow. Look forward to meeting you there again. And a very special thanks to our entire behind the scenes team for enabling such virtual meets and keeping us all connected. Complexity or not, you truly prevent us from running into a chaos. So thank you to everyone. And until we meet again, goodbye and good luck.